Morning Anonymous. We're currently in Darling at Swayze's. I'm joined by David from Mewa. David, thank you for joining us and having a chat.
Pleasure.
So, can you tell us a bit about what you guys offer and what you guys do?
We mostly focus on what we call mass timber engineering, and which is different to timber engineering of 25 years ago because it involves laminating, curving, shaping. So 50 years ago, when big timber was being built, it was built with massive solid beams, and it wasn't shaped. So you were limited by your engineering and your architecture. Today, with modern adhesive, different engineering, we curve timber. So we curve timber, and then we build structures using mechanical and structural engineering backgrounds. We curve timber into structures. So an example would be we built the Greenpoint Dome. So the Greenpoint Dome was a City of Cape Town project, and it's the first mass timber dome built in South Africa, built with massive curved beams. And it's the first perfectly three-dimensional dome in the world.
Oh, wow.
So timber dome. So timber doesn't get curved in 3 dimensions. Timber curves in 2 dimensions because we can fold it, but we can't twist it. So we can shape beams into 3 dimensions, but the roof of the dome was made in ply, and ply doesn't bend 3 ways, it only bends 2 ways. So when we were given the project, the architect asked us, can we bend 3 directions? Mathematically, it's possible. It's just nobody's ever done it. So we said yes. And we bent it in 3 directions, which made it literally structurally incredible, and then a worldwide first. So it's become a public classroom owned by the City of Cape Town, used for events and teaching. And again, nobody seems to, we finished it 2 years ago, nobody's replicated the 3-dimensional dome yet.
So a bit of a hidden secret.
No, it's not a hidden secret at all. I've given the information out there. I've put out there anybody that wants to know how to do it mathematically. It's free knowledge. All knowledge is free, as far as I'm concerned. So we then went on to, we got selected to build a project up at Addo Park, which was what is long name, free-formed, freestanding. It was a hybrid of cross-laminated timber and glue-laminated timber, which people don't do. You do either cross-laminated timber, and most cross-laminated timber is used for floors or walls. It's not a terribly new concept, but it's a new concept in construction. It's the same way as a plyboard is made. You cross different pieces of veneer, and now we're doing the solid wood. So it has become the worldwide trend for tall timber construction, big timber construction. So we used that concept, but we meshed it in with laminated timber so we could curve and shape. So these structures are enormous pergolas on a private nature reserve, each outside the chalets, and they float. The best part of the engineering is they literally freestand. They don't float. They have 3 legs, and they flex in the wind. They move continually. So the engineering was to create an elegant structure that was flexible, not a heavy structure that needed a lot of support. So we built 13 of them and installed them high on top of a mountain. We had many high learning curves because our first experiment was at the bottom of a valley, which worked. And once we went to the main site, which was on top of a mountain where the lodge was, the wind shear factors were phenomenal. We realized that the structure would snap. So the architect didn't allow us a bigger structure. The structure was now cast. So we had to re-engineer the timber to allow for enormous wind shear and weight, because once it's pouring with rain and windy, the structure almost doubles its weight. And we did. We broke into new engineering. We changed the angle of cross-laminating. Cross-laminating is done 90 degrees by 90 degrees. And we changed it to 60 degrees. So we allowed for massive downward loading and sideways movement and kept the shape. Increased the structure strength by more than 200%.
Okay.
So it was a wing and a prayer, based in engineering. So these are the sort of things that we've done. We were on that project for 18 months. We pre-manufactured everything in Darling, assembled every single structure, then took it to pieces, transported to the Eastern Cape and reassembled it on top of every building. And then the final one was there was a hotel. So these structures were size-wise 12 meters by 6 meters in footprint and then about 4.7 meters high. The hotel was 21 meters by 8 meters, and that's at 8 meters high. So 3 times the weight, and it only floated on 4 points. And again, when we assembled it, we had a massive scaffold holding it. And when we took the scaffold away, everybody held their breath.
Very tense.
And it didn't move by a millimeter. So we were lucky. We engineered carefully.
Yeah.
We teach very carefully so that everybody knows their task. We investigate the correct adhesives, the correct timbers. We test structural strength. We don't do normal woodwork. Everything is based in very deep engineering.
And obviously with this type of manufacturing engineering that you guys do, it comes from a very large history and long history of a lot of knowledge being passed down as well. You said your grandfather started this in 1926.
Yeah, 100 years ago.
100 years ago.
So my grandfather was an interesting man, more interesting than we're 5 generations of engineers. So my great-grandfather was Paul Kruger's mining engineer, believe it or not. My grandfather left school when he was 14. They just couldn't afford to let him carry on being at school, and he went and worked as a bricklayer's assistant. And then at about 17, he made his way to Cape Town alone and apprenticed himself to an engineering company, put himself through school at Saks night school, and then went to Technikon, became an engineer, then went on to university, became a further engineer, and then started his own business. And then he continually taught. So he taught at the Technikon every week, besides running his business. So he started off, and he pioneered stainless steel in South Africa, shaping and welding stainless steel, which had never been done. And the business continued for generations. My father and his brother took over, and eventually I took over and changed the elements away from steel
to wood,
to timber.
And that transition, how long did it take, and what complications do you get from obviously switching a complete different...
It was not really that complicated. The stainless steel section was sold off to what was then City Metal Group, which then became Frankie Steel. Okay. So you've seen Frankie Sinks. And so we were open to all types of engineering. I preferred heavy steel, and we built floating steel structures, buildings, all sorts of things. Timber's always been a passion, but moving to Darling, I bought an old Victorian house and discovered that there was nobody that could restore the woodwork, and that kind of sped it up. And as you discovered that there was the engineering of old houses was superb and lost. And so yes, it is an enormous amount of inherited knowledge. My father facilitated learning, taught me, allowed me to read. My engineering library dates back to my grandfather's books. So problems now that we encountered on building the Greenpoint Dome, there was no handbook. There is no handbook for building a mass timber dome anywhere on the planet. There's certain amount of portions, but ultimately you've got to draw everything together. And many of the answers came from books dating to the 1930s. And from there, the knowledge is no longer in books. And today we don't even use books. So today we're reliant on the internet and AI. So A lot of inherited knowledge and a genetic skill, a genetic gift.
Yeah, and I think the way you explained it as well is that knowledge has all been passed down to you, and now yourself as well, you focus on continuing that and sharing that knowledge.
Well, it was an interesting lesson given by my father when I had finished studying. His first question to me was, can you teach all this mathematics that you love to a 6-year-old? And the answer was no. And so he said, well, I think you should go and teach. So I became a teacher. I went and studied a higher diploma in education, and I became a maths and science teacher. And I learned to simplify mathematics, and I learned to teach it. I taught matrics, but I still learned to teach complex mathematics into simplified version of real life.
Yeah.
So when you get a formula from a teacher, I gave the real life version. And it was the best. It was the most learning I'd done in my entire life.
I think that's a great tool to have, because a lot of people get lost in that complication.
Well, that's it. Mathematics is not complicated. Mathematics is actually excessively simple and ancient.
Yeah.
So if you take complex mathematics, such as the green point dome, and you bring it down to its lowest common point, it's actually understandable. So to give you an idea of where mathematics got lost, is we were not given the brief of the green point dome to build the roof. The roof sheeting was to look, the dome was dedicated to the Khoi people. So it's a very big hut. It was meant to look like skins. So it was different pieces of steel painted to different colors so that it had a hut look. But it's a perfectly three-dimensional dome. So we can't go random. We have to go geometric, but it has to look random. So perfectly randomly geometric.
Yeah.
And we had consulting engineers, and eventually the discussion started about the roof covering. We had already chosen what steel to use, which is a compound called 3CR12, which is a South African design. It's a mixture of stainless steel and steel. It doesn't rust. But now how do we lay it? So we had a computer AI rendering, but we had no plans. So we use a computer-assisted drawing program called Revit, which is extremely powerful. And Revit couldn't draw a 3D roof for us on a dome. It wasn't in the software. You know, if you've never programmed the software, it's not going to draw it.
Yeah.
And nobody's ever built a 3D roof in sheets of steel. So we had to work out how to build. I kept quiet for at least 2 weeks until it was then given to me and saying, okay, solve the problem. And the problem was actually excessively simple. It was mathematics that we don't learn any longer, and it's called spherical geometry. Spherical geometry was used to map the Earth, lines of longitude and latitude.
Yeah.
But come World War I, we had airplanes and we photographed the Earth. So we didn't need to map it anymore. And as years have gone by, we now have Google Earth. We don't need, we learn it in school, lines of latitude and longitude, but we don't realize that it's a piece of geometry.
Yeah.
So using spherical geometry, I then designed the roof in latitude lines, which were even, but the longitude lines are staggered. So every line was in a different space. So it looked random, but it was geometrically perfect. And we still couldn't draw it on a computer, so I drew it by hand, flat, with a drawing board. What was fascinating and incredibly forward-thinking was, so let me go back to the actual mathematics came out of a textbook published in 1936 in Oxford University. From then I couldn't find the mathematics published in a textbook because they stopped teaching it. We didn't need it anymore. It was a piece of mathematics that's no longer, and if you go onto the internet, there are maybe a half a page on it. But the real mathematics, the formulas, and meshing the formulas together is gone.
And how long did that process take you to figure out?
Actually, just a couple of days. It was, having been a Boy Scout, I loved map reading. So that it was immediately apparent that it was lines of that. It was in Earth. It was a half an Earth.
Yeah.
So how do you map it? You know, don't think about drawing, I think about mapping it. So how would you map an Earth with lines of latitude and longitude? Just change longitude lines.
So it just made sense from the
get-go. It made sense. Most of the engineering actually does make sense. It's all based in mathematics, which is all very simple. And how do you simplify it? You learn to teach it.
Yeah.
If you teach mathematics, you simplify mathematics. So always, my logic is always, how do you teach complex things to people who have no knowledge or have no previous education? Yeah. And they get it. All the people that work for me can do maths now. They can work out square, and they can work out the area of a circle, things that they did learn in school, but they didn't understand anything about it. Now they see it in real life, and they can work it out. So that was just an example of old mathematics, passed down engineering, and a way of thinking.
Now, if anyone wants to get hold of you guys for projects, learning, or anything like that, how do they go about it?
Well, we're on the internet. There is a Mewa website, just mewa.co.za, and there are contact details, and obviously pictures of our projects that we do. And that's the easiest way to get a hold of us. I don't accept all projects, but I do assist people. There have been companies who have come and asked us to teach them how to bend a beam in 3 directions. So we teach them how. They'll pay for a consulting time, and we let them do the manufacture. Okay. So to try and pass the engineering,
so offer that as well.
To try and get it bigger. We don't want every project. We want to pass on the knowledge.
And see the whole industry grow, rather than just yourself.
Well, we're watching mass timber grow in South Africa in the last 2 years more than 400%. So the mass timber industry is growing enormously and quickly. We're seeing knowledge, we're seeing people changing their systems, we're seeing overseas investment come into the country, and we're seeing architects realize that timber's not a substitute material, it's its own material.
Yeah.
So you can't speak about timber in the language of concrete and steel. Timber's got its own language. So once you realize that timber is not a substitute material, it's its own material, you can virtually make anything.
Incredible.
So,
David, thanks so much for sitting down, chatting to us.
Okay.
I think there's been a lot learned just from this brief conversation. I'm sure we could probably speak for hours.
Yes, you could, yeah.
But thank you so much for your time. We do appreciate it.
Pleasure.
We wish you nothing but the best.
Thank you.
And we'll add all your details at the end of the video.
Excellent.
Thank you very much.
Pleasure.
See you guys next time.
Okay.